Imagine if you could travel 1 light-year per second. In 60 seconds, you'd witness the birth and death of stars, watch galaxies collide in fast forward, and see things that exist in dimensions your brain wasn't built to process. This impossible journey would compress billions of years of cosmic travel into a human lifetime. If you are curious about these crazy scenarios, please subscribe to the channel. We're embarking on this mind-bending voyage together. Now let's get started. At this impossible speed, the fundamental nature of space and time would warp beyond recognition. The stars ahead of you wouldn't just appear to move. They would undergo a dramatic shift in color due to the most extreme Doppler effect imaginable. Every photon of light from stars in front of you would be compressed to wavelengths far beyond human vision. The familiar constellations would vanish, replaced by an alien sky painted in impossible colors. But here's where our journey gets truly strange. At 1 light-year per second, you're not just moving through space, you're essentially time traveling. The light reaching your eyes from distant objects left those sources at different times in cosmic history. As you race through the universe at this impossible velocity, you'd be witnessing cosmic evolution in fast forward, watching billions of years of galactic history compressed into moments. Let's start our voyage from Earth in our familiar solar system. In less than a heartbeat at our impossible speed, you'd flash past the orbit of Neptune, leaving our sun as nothing more than a rapidly dimming point of light behind you. The Voyager spacecraft, humanity's most distant ambassadors currently cruising through interstellar space after 46 years of travel, would be passed in an infinitesimal fraction of a second. Within just 4 seconds of your departure, you'd reach Proxima Centauri, our nearest stellar neighbor. But at your velocity, you wouldn't see it as the red dwarf star familiar from astronomy textbooks. Instead, the extreme blue shifting of its light would transform it into a blazing beacon of high-energy radiation. Any planets orbiting this star, including the potentially habitable Proxima Centauri b discovered in 2016, would be invisible, their reflected light shifted far beyond any wavelength your instruments could detect. The Oort cloud, that vast spherical shell of icy bodies that marks the true boundary of our solar system, extends nearly 2 light-years from the Sun. Astronomers estimate it contains trillions of cometary nuclei, frozen remnants from our solar system's formation 4.5 billion years ago. At normal speeds, it would take spacecraft tens of thousands of years to traverse this region. You'd cross it in less than 2 seconds, though the sparse distribution of objects means you'd likely see nothing but the distorted starlight ahead. As you continue your impossible journey, you'd encounter one of the most profound realizations about the universe. It is overwhelmingly empty. The vast gulfs between stars would become viscerally apparent as you spend second after second racing through absolute nothingness. Space isn't just big, it's incomprehensibly vacant, with matter concentrated in tiny islands separated by cosmic voids that dwarf human imagination. 10 seconds into your journey, you'd have traveled 10 light-years from Earth. The stars within this sphere include some of the most studied objects in astronomy. Epsilon Eridani, a young star system where astronomers have detected at least one planet and possibly asteroid belts similar to our own. Tau Ceti, long a favorite of science fiction writers and SETI researchers searching for extraterrestrial intelligence. Each of these systems would flash by too quickly to observe, their light transformed into alien spectra by your impossible velocity. But something strange would be happening to your view of the universe. The cosmic microwave background radiation, that faint afterglow of the Big Bang that fills all of space, would be dramatically blue shifted in the direction of your travel. This ancient light, normally invisible to human eyes and detectable only by sensitive radio telescopes, would be compressed into visible and even ultraviolet wavelengths. You'd literally be seeing the echo of creation itself, transformed by your motion into a blazing wall of primordial light. 20 seconds out, 20 light years from home, you'd be passing through a region of space containing several fascinating stellar systems. Gliese 667c, a super-Earth exoplanet that orbits within its star's habitable zone. The binary star system of Alpha Centauri A and B, locked in their eternal gravitational dance. Each of these systems represents potential homes for life, worlds where complex chemistry might have evolved into biology, but at your speed, they're nothing more than streaks of impossibly shifted light. The psychological impact of this journey would be as profound as the physical phenomena. Watching familiar stars disappear and new ones emerge from the cosmic background would drive home the reality that Earth, our entire solar system, everything we've ever known, is just one tiny corner of an incomprehensibly vast universe. The comfortable illusion that we exist at the center of everything would shatter completely as you realized that every point in space could equally claim to be the center, and none of them would be wrong. 30 seconds into your voyage, you'd have covered 30 light years, entering a region of space where the stellar neighborhood becomes less familiar. The stars here have been studied by telescopes, their properties catalogued by astronomers, but they're not the bright beacons visible to the naked eye from Earth. You're entering the true stellar wilderness, where each star might harbor its own system of planets, its own potential for life, its own billion-year history of cosmic evolution. As you reach the 1-minute mark of your impossible journey, you've traveled 60 light years from Earth, and the transformation of your cosmic perspective becomes complete. The Sun, our life-giving star that has anchored human existence for millions of years, would be utterly invisible, lost among countless other points of light. Earth itself would be less than a mote of dust, undetectable by any conceivable instrument. The radio signals from our planet, carrying our music, our conversations, our declarations of love and war, would be 60 years out of date by the time they reached your current position. But here's where the physics of your impossible journey creates a paradox that would make even seasoned physicists pause. At 1 light year per second, you're traveling about 31,500,000 times the speed of light. According to Einstein's special relativity, this should be impossible. Nothing with mass can even reach light speed, let alone exceed it. Yet for our thought experiment, we're imagining what such a journey would reveal about the structure and content of our universe. The galaxy around you would no longer resemble the serene spiral we see in astronomy textbooks. The Milky Way contains between 200 and 400 billion stars, spread across a disk roughly 100,000 light-years in diameter. At your impossible speed, you could cross our entire galaxy in just 100 seconds, less than 2 minutes. But the view would be anything but peaceful. Stars would appear and disappear like cosmic fireflies as you race through the galactic disk. The spiral arms, those regions of enhanced star formation where young, hot stars illuminate vast clouds of gas and dust, would strobe past in patterns of light and darkness. The interstellar medium, usually invisible to the naked eye, would glow with induced radiation as your impossible velocity energizes the sparse atoms and molecules in space. 2 minutes into your journey, 120 light-years from Earth, you'd be encountering stellar populations that tell the story of our galaxy's evolution. Old red giants, bloated stars in their death throes, would mark where earlier generations of stars are ending their lives. Young blue supergiants burning through their nuclear fuel at prodigious rates would blaze as with the intensity of millions of suns. Each star you pass represents a unique experiment in stellar evolution, a test of how matter and energy interact under extreme conditions. The variety of stellar systems would be staggering. Binary stars locked in gravitational embraces, their mutual orbit causing them to eclipse each other in regular patterns. Multiple star systems where 3, 4, or even more stars dance in complex gravitational choreographies. Planetary systems of every conceivable configuration. Hot Jupiters orbiting closer to their stars than Mercury orbits our Sun. Super-Earths with compositions unlike anything in our solar system. Ice giants in distant orbits where water freezes harder than rock. Recent discoveries from the Kepler Space Telescope and its successor, TESS, the Transiting Exoplanet Survey satellite, have revealed that planets are the rule rather than the exception. Nearly every star you'd pass likely hosts at least one planet, and many have complex systems rivaling or exceeding our own in richness. The James Webb Space Telescope has even detected atmospheres around some of these worlds, finding water vapor, methane, and other molecules that hint at the incredible diversity of planetary environments. 3 minutes out, 180 light-years from home, you'd be passing through regions where stellar archaeology reveals the galaxy's deep history. Some stars here are ancient, formed when the universe was only a few billion years old and heavy elements were scarce. These metal-poor stars represent stellar fossils, preserving information about conditions in the early galaxy. Other stars are young, perhaps only a few million years old, still surrounded by the protoplanetary disks from which planets are actively forming. The distribution of stars would tell you about the galaxy's structure. You'd notice that stars aren't scattered randomly, but follow patterns carved by gravity over billions of years. Stellar streams mark where smaller galaxies were torn apart and absorbed by the Milky Way. Star clusters, both the ancient globular clusters that orbit in the galactic halo and the young open clusters born in spiral arms, would flash past like glittering jewels. 4 minutes into your journey, 240 light-years traveled, you'd begin to appreciate the true three-dimensional structure of our galactic neighborhood. The local bubble, a region of relatively empty space carved out by ancient supernovae, would reveal itself through the sudden decrease in interstellar dust and gas. This cosmic void, roughly 300 light-years across, has shaped the distribution of nearby stars and may have influenced the formation of our own solar system. The hazards of interstellar space would become apparent at your impossible velocity. Dust grains, normally insignificant specks drifting between stars, would impact your vessel with the energy of nuclear weapons. The sparse hydrogen atoms of the interstellar medium would create a constant bombardment of radiation. Even the cosmic rays, high-energy particles accelerated by supernovae and other violent events, would pose extreme challenges to both spacecraft and any biological passengers. Speaking of interstellar space, have you ever wondered how long we could survive real interstellar travel? Click the video on the card above and discover why the real horror of interstellar travel isn't the vast distance. It's what deep space does to the human body and mind. We break down the brutal biological, psychological, and physical barriers that make human interstellar travel practically impossible. The video is pinned on the comments. 5 minutes out, 300 light-years from Earth, you'd be entering regions where the night sky visible from any planets would be dramatically different from our own. The constellations that have guided human navigation and mythology for millennia would be unrecognizable. Bright stars like Sirius and Canopus would appear in entirely different positions, while new stars, invisible from Earth, would dominate alien skies. This brings us to one of the most profound realizations of your journey. The universe has no preferred perspective. Every location in space has its own unique view of the cosmos, its own set of neighboring stars, its own cosmic horizon. The universe looks different from every vantage point, yet the same physical laws govern all of it. This cosmic democracy of perspectives challenges our instinctive belief that our view of the universe is somehow special or central. 6 minutes into your impossible voyage, 360 light-years traveled, you'd be passing through regions where recent supernovae have sculpted the interstellar medium into vast bubbles and shells. The Vela supernova remnant, the local bubble and other structures created by stellar explosions, would reveal how dying stars shape the galaxy for future generations. These cosmic catastrophes, violent enough to outshine entire galaxies, are also cosmic gardens where new stars and planets can form from enriched material. The chemical evolution of the galaxy would be written in the stars you pass. Each generation of stars creates heavier elements through nuclear fusion, then disperses them through stellar winds and supernova explosions. The metallicity gradient of the galaxy, the way heavy element abundance changes with distance from the galactic center, tells the story of billions of years of stellar birth and death, a cosmic recycling program that eventually produced the elements necessary for planets and life. 7 minutes into your impossible journey, 420 light-years from Earth, you'd encounter one of the most beautiful and scientifically important regions of our galaxy, stellar nurseries. The Orion Nebula, visible as a fuzzy patch to the naked eye from Earth, would reveal itself as a vast, star-forming region spanning dozens of light-years. At your incredible velocity, you'd flash through this cosmic maternity ward in seconds, but what you'd witness would be breathtaking. Young protostars, still gathering mass from their surrounding disks, would glow with the heat of gravitational contraction. Jets of material, launched from the poles of these infant stars, would stretch for light-years, carving glowing cavities in the surrounding nebula. The Hubble Space Telescope has captured stunning images of these protostellar jets, but experiencing them at your speed would be like watching a time-lapse of stellar birth compressed into heartbeats. The nebula itself would be a riot of color and activity. Hydrogen gas, ionized by the intense ultraviolet radiation from hot young stars, would glow with its characteristic red emission. Dust grains, heated by starlight, would emit infrared radiation that your impossibly advanced spacecraft could detect. The complex organic molecules found in these regions by radio telescopes, including formaldehyde, methanol, and even simple amino acids, represent the building blocks from which life might eventually emerge on newly formed planets. 8 minutes out, 480 light-years traveled, you'd be moving through regions where planetary formation is actively occurring. The protoplanetary disks surrounding young stars, imaged in spectacular detail by the Atacama Large Millimeter Array in Chile, would flash past like cosmic pizza dough being shaped by gravity. Within these disks, dust grains collide and stick together, gradually building up the planetesimals that will eventually become planets. The diversity of these forming systems would be staggering. Some disks show clear gaps where planets have already formed and cleared their orbits. Others display spiral patterns, suggesting gravitational interactions with massive planets or companion stars. The James Webb Space Telescope has even detected water vapor and other molecules in these disks, revealing that the ingredients for habitable worlds are present from the very beginning of planetary formation. 9 minutes into your voyage, 540 light-years from home, you'd encounter stellar associations, loose groups of stars that formed together from the same molecular cloud. These stellar siblings, bound by their common origin rather than gravity, would be slowly drifting apart, destined to become isolated stars like our Sun. The Pleiades, visible as a beautiful cluster from Earth, represents one such association in its youth. While older groups have already dispersed across the galaxy, the realization that our Sun likely formed in such a cluster, surrounded by stellar siblings that have long since scattered across the galaxy, adds a poignant note to your journey. Somewhere among the billions of stars in the Milky Way are the Sun's brothers and sisters, formed from the same cloud of gas and dust 4.5 billion years ago. Your impossible speed might take you past some of these lost relatives, but there would be no way to recognize them among the stellar multitudes. 10 minutes out, 600 light-years traveled, you'd be encountering some of the galaxy's most extreme objects. Neutron stars, the ultra-dense remnants of massive stars that exploded as supernovae, would reveal themselves through their intense magnetic fields and rapid rotation. Pulsars, neutron stars that sweep lighthouse beams of radiation across space, would strobe past like cosmic lighthouses, marking the graves of giant stars. The physics of these objects pushes the boundaries of human understanding. A neutron star packs more mass than our Sun into a sphere just 20 kilometers across. The gravity at their surface is so intense that a marshmallow dropped from a height of 1 meter would impact with the energy of an atomic bomb. The magnetic fields around some neutron stars are so strong they would rip the iron from your blood at a distance of thousands of kilometers. 11 minutes into your journey, 660 light-years from Earth, you'd encounter your first stellar mass black holes. These invisible monsters, formed when the most massive stars collapse at the end of their lives, would reveal themselves only through their effect on surrounding matter. Binary systems where a black hole feeds on a companion star would glow with X-rays as matter spirals toward the event horizon, heating to millions of degrees in its final plunge toward oblivion. The discovery of gravitational waves by LIGO and Virgo has opened an entirely new window on these extreme objects. When black holes merge, they send ripples through spacetime itself, stretching and compressing the fabric of reality as they pass. At your impossible speed, you might traverse regions of space, still reverberating with gravitational waves, from ancient mergers, cosmic earthquakes that happened millions or billions of years ago. 12 minutes out, 720 light-years traveled, you'd be passing through regions where the galaxy's spiral structure becomes apparent. The spiral arms aren't solid structures but rather density waves, regions where stars and gas bunch up temporarily before moving on. Like traffic jams that persist even as individual cars move through them, these density waves trigger star formation as gas clouds are compressed, creating the bright spiral patterns we see in galaxies throughout the universe. The Sun and Earth currently reside between major spiral arms in a relatively quiet region called the local spur. But at your speed, you'd quickly pass through the Perseus arm, one of the galaxy's major spiral features. The contrast would be dramatic. Regions of intense star formation, massive molecular clouds, and clusters of brilliant young stars would give way to quieter inter-arm regions where older stars predominate. 13 minutes into your impossible voyage, 780 light-years from home, you'd encounter evidence of the galaxy's violent past. Stellar streams, long chains of stars torn from smaller galaxies that ventured too close to the Milky Way, would trace arcs across your path. These cosmic fossils tell the story of galactic cannibalism, how large galaxies grow by consuming smaller ones over billions of years. The Sagittarius dwarf galaxy, currently being torn apart by the Milky Way's gravity, has left streams of stars wrapped around our galaxy multiple times. The Gaia Space Telescope has mapped these streams in exquisite detail, revealing how our galaxy has grown and evolved through cosmic mergers. Your journey would take you through these stellar rivers, past stars that once belonged to entirely different galaxies before being captured by the Milky Way's gravitational embrace. 14 minutes into your cosmic race, 840 light-years from Earth, you'd encounter one of the most mysterious components of our galaxy, dark matter. While invisible to all forms of electromagnetic radiation, dark matter makes up roughly 85% of all matter in the universe. Its gravitational influence shapes the galaxy, creating an invisible scaffolding that guides the distribution of stars and gas. The evidence for dark matter would be all around you, encoded in the motions of the stars you pass. Stars orbiting far from the galactic center move faster than they should if only visible matter were present. This was first noticed by astronomer Vera Rubin in the 1970s, and it revolutionized our understanding of the cosmos. Your impossible journey would take you through the dark matter halo that surrounds our galaxy, an invisible sphere of mysterious particles that dwarfs the visible disk. 15 minutes out, 900 light-years traveled, you'd be passing through regions where the interstellar medium tells stories of cosmic recycling on a grand scale. Supernova remnants, expanding shells of gas heated to millions of degrees, would mark where massive stars ended their lives in titanic explosions. The Crab Nebula, created by a supernova observed by Chinese astronomers in the year 1054, would flash by as an expanding cloud of glowing gas with a pulsar at its heart, spinning 30 times per second. These stellar explosions are the universe's element factories. While stars like our Sun can only create elements up to carbon and oxygen through normal fusion, the extreme conditions in supernovae forge heavier elements all the way up to iron. Elements heavier than iron, including the gold in jewelry and the uranium that powers nuclear reactors, are created in the final moments of these cosmic catastrophes, or in the collision of neutron stars. 16 minutes into your journey, 960 light-years from home, you'd encounter planetary nebulae, the beautiful death shrouds of sun-like stars. Despite their name, these objects have nothing to do with planets. They form when dying stars shed their outer layers, creating intricate shells of glowing gas illuminated by the hot stellar core left behind. The Ring Nebula, the Cat's Eye Nebula, and other famous examples would reveal themselves as three-dimensional sculptures of gas, shaped by stellar winds and magnetic fields. The fate of our own Sun is written in these cosmic ghosts. In about 5 billion years, our star will exhaust its nuclear fuel and begin its transformation into a red giant. It will shed its outer layers, creating its own planetary nebula while its core contracts to become a white dwarf. Your impossible journey shows you countless examples of this stellar life cycle, each one a preview of our Sun's distant future. 17 minutes out, 1,020 light-years traveled, you'd be entering regions where the galaxy's magnetic field becomes apparent. This vast magnetic structure, mapped by observing the polarization of light from distant stars, guides cosmic rays and influences star formation throughout the galaxy. The magnetic field lines would be invisible to your eyes, but their effects would be everywhere, in the alignment of dust grains, the propagation of supernova shockwaves, and the trajectories of charged particles. Recent observations by the Planck Space Telescope have revealed that magnetic fields play a crucial role in shaping the interstellar medium. They can support molecular clouds against gravitational collapse, delaying star formation, or channel gas flows that feed stellar nurseries. Your journey would take you through regions where these invisible forces sculpt the visible universe in ways we're only beginning to understand. 18 minutes into your impossible voyage, 1,080 light-years from Earth, you'd encounter evidence of one of the most exciting frontiers in modern astronomy, the search for extraterrestrial intelligence. The SETI Institute and other organizations have been scanning the skies for decades, looking for artificial signals that might indicate the presence of technological civilizations. At your speed, you'd be passing through the water hole, the quiet region of the radio spectrum where hydrogen and hydroxyl emissions create a natural cosmic quiet zone ideal for interstellar communication. The Drake equation, formulated in 1961, attempts to estimate the number of communicating civilizations in our galaxy. With hundreds of billions of stars, many hosting planets in their habitable zones, the potential for life seems enormous. Yet the Fermi paradox, the puzzling absence of obvious signs of alien civilizations, remains one of the most profound mysteries in science. Your journey might take you past worlds where intelligence has emerged, but at your impossible speed, any signals would be shifted far beyond recognition. 19 minutes out, 1,140 light-years traveled, you'd be passing through regions where binary star evolution creates some of the most exotic objects in the universe. When two stars orbit each other closely, they can exchange mass, leading to phenomena like X-ray binaries, cataclysmic variables, and Type Ia supernovae. These binary interactions are cosmic laboratories where matter behaves in extreme ways, producing radiation across the entire electromagnetic spectrum. The discovery of merging neutron stars through gravitational waves has revealed that these binary systems are also cosmic alchemists. The collision detected in 2017, designated GW170817, created and dispersed heavy elements equivalent to many Earth masses of gold and platinum. These kilonovae, as such events are called, may be responsible for creating much of the universe's supply of the heaviest elements. 20 minutes into your journey, 1,200 light-years from home, you'd be approaching regions where globular clusters orbit the galaxy. These ancient stellar cities contain hundreds of thousands of stars packed into spheres just a few dozen light-years across. The stars in globular clusters are among the oldest in the universe, formed when the galaxy itself was young. They orbit in the galactic halo, following paths that take them high above and below the disk. The density of stars in globular cluster cores is extraordinary. While stars near the Sun are separated by several light-years, stars in cluster cores might be separated by just light weeks or light months. From a planet orbiting a star in such a cluster, the night sky would blaze, with thousands of stars brighter than Venus appears from Earth. The gravitational interactions in these crowded environments create exotic objects like blue stragglers, stars that appear younger than they should be because they've merged with or stolen mass from companions. 21 minutes into your impossible voyage, 1,260 light-years from Earth, you'd witness one of nature's most spectacular light shows, gamma-ray bursts. These cosmic explosions, the most energetic events in the universe since the Big Bang, release more energy in seconds than our Sun will produce in its entire 10-billion-year lifetime. The Swift satellite and Fermi Gamma-ray Space Telescope have detected thousands of these events, revealing two distinct types: short bursts from merging neutron stars and long bursts from the collapse of massive stars. At your incredible speed, you might pass through the expanding shells of radiation from ancient gamma-ray bursts, experiencing firsthand the most violent explosions the universe can produce. The physics of these events pushes our understanding to its limits. Matter accelerated to 99.999% the speed of light, magnetic fields trillions of times stronger than Earth's, and temperatures that recreate conditions from the first seconds after the Big Bang. 22 minutes out, 1,320 light-years traveled, you'd be encountering Wolf-Rayet stars, massive stellar giants in their death throes. These rare objects, perhaps only a few hundred in our entire galaxy, represent stars so massive and hot that they're literally blowing themselves apart. Their stellar winds, traveling at thousands of kilometers per second, carry away mass at rates millions of times greater than our Sun's gentle solar wind. The spectra of Wolf-Rayet stars tell stories of extreme physics. Surface temperatures exceeding 50,000 degrees Celsius strip away hydrogen, revealing layers rich in helium, carbon, nitrogen, and oxygen, the ashes of nuclear fusion exposed to space. These stars are ticking time bombs destined to explode as supernovae or possibly even hypernovae. events so violent they can be seen across billions of light years. 23 minutes into your journey, 1,380 light years from home, you'd enter regions where stellar archaeology reveals the galaxy's chemical evolution in exquisite detail. The oldest stars you'd encounter contain almost no elements heavier than hydrogen and helium, preserving the primordial composition of the early universe. These ancient suns formed when the galaxy was young, before generations of supernovae had enriched the interstellar medium with heavier elements. The Sloan Digital Sky Survey and other massive observational programs have catalogued millions of stellar spectra, creating a chemical map of our galaxy. Each star's spectrum is like a barcode, revealing not just its temperature and composition, but also clues about where and when it formed. Your journey would take you through this chemical gradient, from metal-rich regions near the galactic center to metal-poor areas in the outer halo. 24 minutes out, 1,440 light-years traveled, you'd be passing through regions where microquasars demonstrate black hole physics on stellar scales. These binary systems, where a black hole or neutron star pulls matter from a companion star, create jets of material moving at significant fractions of light speed. Unlike their supermassive cousins in distant galaxies, these microquasars let us study relativistic jet physics in our own cosmic backyard. The system SS-433 in the constellation Aquila shoots out jets that appear to move faster than light, an illusion created by material moving at relativistic speeds almost directly toward us. Radio telescopes have tracked these jets over years, watching knots of material race away from the central black hole. At your impossible speed, you might pass right through these jets, experiencing conditions where matter and energy behave according to Einstein's most extreme predictions. 25 minutes into your impossible voyage, 1,500 light-years from Earth, you'd encounter molecular clouds of staggering size and complexity. The Orion Molecular Cloud Complex, spanning hundreds of light-years, contains enough material to form millions of stars like our Sun. Within these vast clouds, chemistry happens on cosmic scales, with molecules ranging from simple carbon monoxide to complex organic compounds that might seed life on newborn planets. Radio telescopes have detected over 200 different molecular species in these interstellar clouds, including alcohols, sugars, and even amino acids. The cold temperatures, often just 10 or 20 degrees above absolute zero, allow these fragile molecules to survive and slowly react, building complexity over millions of years. Your journey through these clouds would be like flying through a cosmic chemistry laboratory where nature experiments with the building blocks of life. 26 minutes out, 1,560 light-years traveled, you'd be witnessing stellar interactions that challenge our understanding of how stars evolve. Blue straggler stars, which appear younger and hotter than they should be given their age, reveal that stellar collisions and mergers can reset a star's evolutionary clock. In dense stellar environments, stars can literally collide and merge, creating objects that don't fit neatly into our theoretical models. Recent observations by the Hubble Space Telescope have caught these stellar mergers in action. In the globular cluster NGC 6397, astronomers discovered stars in the process of merging, their outer atmospheres already mingling as gravity pulls them together. These cosmic train wrecks happen in slow motion by human standards, taking thousands of years to complete, but at your speed, you'd witness the entire process compressed into moments. 27 minutes into your journey, 1,620 light-years from home, you'd encounter runaway stars, massive stars ejected from their birthplaces at tremendous velocities. Some of these stellar speedsters race through space at hundreds of kilometers per second, fast enough to eventually escape the galaxy entirely. They leave behind bow shocks, glowing arcs of compressed gas that mark their passage through the interstellar medium. The origins of these runaway stars tell violent stories. Some were ejected from binary systems when their companions exploded as supernovae. Others were gravitationally slingshot out of dense star clusters through three-body interactions. The star Zeta Ophiuchi, visible to the naked eye from Earth, is one such runaway, plowing through space at 24 kilometers per second and creating a spectacular bow shock visible in infrared light. 28 minutes out, 1,680 light-years traveled, you'd be passing through regions where the galaxy's history of violence is written in stellar streams and tidal debris. The remains of dwarf galaxies consumed by the Milky Way create rivers of stars that can stretch for thousands of light years. The Gaia Space Telescope has revealed dozens of these streams, each one a ghost of a galaxy that ventured too close to our own. These galactic mergers aren't just ancient history. The large and small Magellanic Clouds, visible from Earth's southern hemisphere, are currently interacting with our galaxy. Gas stripped from these satellite galaxies forms the Magellanic Stream, a river of hydrogen gas stretching across more than half the sky. Your journey might take you through this cosmic debris field, evidence that galaxies grow through cosmic cannibalism that continues to this day. 29 minutes into your impossible voyage, 1,740 light-years from Earth, you'd encounter evidence of one of the most mysterious phenomena in modern astronomy: fast radio bursts. These millisecond-long pulses of radio waves release as much energy as the sun emits in days, yet their origins remained unknown for years after their discovery. The Chime Telescope in Canada and the Parkes Observatory in Australia have detected hundreds of these cosmic flashes, some repeating and others appearing just once. Recent breakthroughs have traced some fast radio bursts to magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. At your speed, you might pass through the expanding shells of radio waves from these bursts, experiencing electromagnetic storms of unimaginable intensity. The fact that we can detect these bursts from other galaxies billions of light-years away speaks to the extraordinary energies involved. 30 minutes out, half an hour into your journey, you've traveled 1,800 light-years. At this distance, you'd be encountering regions where the three-dimensional structure of our galaxy becomes dramatically apparent. The galactic disk isn't perfectly flat, but warped like a vinyl record left in the sun. This warp, likely caused by gravitational interactions with satellite galaxies, means that stars on opposite sides of the galaxy can be thousands of light-years above or below the mean galactic plane. The vertical structure of the galaxy tells its own story. Young hot stars concentrate in the thin disk, while older stars populate the thick disk and halo. The distribution reveals how our galaxy formed through multiple merger events, each adding layers to the galactic structure like geological strata. Your journey would take you through these different populations, each representing a different chapter in the galaxy's 13 billion-year history. 31 minutes into your voyage, 1,860 light-years traveled, you'd witness the galaxy's ongoing battle between gravity and rotation. The spiral arms you're passing through aren't solid structures but density waves where stars and gas temporarily congregate. Like cosmic traffic jams, these waves trigger star formation as gas clouds pile up and collapse. The Spitzer Space Telescope's infrared observations revealed that these density waves travel around the galaxy at different speeds than the stars themselves. This cosmic choreography means that individual stars pass in and out of spiral arms over millions of years. Our Sun has likely passed through major spiral arms multiple times during its 5 billion-year life, experiencing periods of enhanced radiation and increased risk of nearby supernovae. The fossil record on Earth might even preserve evidence of these passages in the form of mass extinction events or climate changes triggered by cosmic radiation. 32 minutes out, 1,920 light-years traveled, you'd encounter stellar graveyards where white dwarfs slowly cool toward cosmic obscurity. These Earth-sized remnants of sun-like stars represent the final stage for 97% of all stars in our galaxy, made of carbon and oxygen compressed to densities where a teaspoon would weigh tons. White dwarfs gradually radiate away their heat over trillions of years. The coolest white dwarfs detected are nearly as old as the galaxy itself, cosmic embers from the first generation of low-mass stars. By studying these ancient remnants, astronomers can determine the age of different stellar populations and trace the history of star formation in our galaxy. Your impossible journey would take you past white dwarfs of every temperature, from recently formed ones glowing hotter than the sun to ancient ones barely warmer than the cosmic background. 33 minutes into your impossible voyage, 1,980 light-years from home, you'd be passing through regions where planetary systems showcase nature's creativity. Hot Jupiters, gas giants orbiting closer to their stars than Mercury to our Sun, challenged our theories of planetary formation when first discovered. Super-Earths with no analogue in our solar system appear to be among the most common types of planets. Water worlds entirely covered in deep oceans, lava planets with surfaces of molten rock, and planets orbiting binary stars like Tatooine from Star Wars all exist within the galaxy. The Kepler Space Telescope and TESS have revealed that planetary systems come in configurations that seem to defy logic. Planets in resonant chains where orbital periods form simple ratios, compact systems with multiple planets orbiting closer than Mercury, and planets on highly elliptical orbits that swing from scorching heat to freezing cold. Each system tells a unique story of formation and evolution, shaped by gravitational interactions, stellar radiation, and cosmic chance. 34 minutes out, 2,040 light-years traveled, you'd encounter regions where stellar feedback shapes the galaxy on vast scales. Massive stars don't just live and die in isolation, they profoundly influence their surroundings throughout their lives. Stellar winds from hot stars can clear cavities dozens of light-years across. When these stars explode as supernovae, they can trigger or suppress star formation across entire regions, creating a complex ecosystem where stellar generations influence each other. The Carina Nebula, one of the most spectacular star-forming regions in our galaxy, showcases this stellar feedback in action. The Hubble Space Telescope has captured images of pillars of gas being eroded by radiation from nearby massive stars, even as new stars form within the pillars. It's a cosmic balance between creation and destruction played out across hundreds of cubic light-years. 35 minutes into your journey, 2,100 light-years from Earth, you'd be witnessing how galaxies maintain their chemical diversity. Different regions of the galaxy have different metallicities, abundances of elements heavier than hydrogen and helium. The galactic center, where stars have been forming for billions of years, is enriched with heavy elements. The outer regions, where star formation has been less intense, preserve more of the primordial composition. This chemical gradient isn't uniform, but shows complex patterns shaped by gas flows, stellar migrations, and localized enrichment from supernovae. The Apogee survey, part of the Sloan Digital Sky Survey, has measured the chemical composition of hundreds of thousands of stars, revealing that stars can migrate significant distances from their birthplaces. Your journey would take you through these chemical provinces, each with its own distinctive stellar populations. 36 minutes out, 2,160 light-years traveled, you'd encounter evidence of the galaxy's most recent meals. Streams of stars from disrupted dwarf galaxies create fossil evidence of past mergers. The Virgo stellar stream, the Monoceros ring, and dozens of other structures reveal that our galaxy has grown by consuming smaller neighbors throughout its history. These mergers don't just add stars, they can trigger bursts of star formation and reshape the galaxy's structure. The process continues today. The Sagittarius dwarf spheroidal galaxy is currently being torn apart by tidal forces, its stars spreading along an orbit that carries them around the entire galaxy. Computer simulations suggest that interactions with this infalling galaxy may have helped create the Milky Way's spiral arms. Your journey might take you through regions where stars from different galaxies mingle, their distinct chemical signatures revealing their foreign origins. 37 minutes into your impossible voyage, 2,220 light-years from Earth, you'd be entering regions where the interstellar medium becomes a dynamic, living entity. Giant molecular clouds don't just sit passively in space. They collide, merge, and fragment in a cosmic dance driven by turbulence, magnetic fields, and gravity. The Herschel Space Observatory revealed that these clouds are threaded with filamentary structures, like cosmic spider webs, where stars preferentially form along the densest strands. The physics of turbulence in these clouds connects the largest scales to the smallest. Supersonic gas flows create shock waves that compress material, triggering gravitational collapse. Yet the same turbulence that enables star formation also fights against it, supporting clouds against gravity. This delicate balance determines where, when, and how stars form throughout the galaxy. Your journey would take you through regions where this cosmic battle plays out across hundreds of light years. 38 minutes out, 2,280 light-years traveled, you'd encounter stellar populations that reveal the galaxy's connection to cosmological evolution. The oldest stars in our galaxy formed when the universe was only a few 100 million years old, from gas that had never been enriched by supernovae. These population 3 stars, as astronomers call them, were likely massive and short-lived, but they fundamentally changed the universe by creating the first heavy elements. While no true population 3 stars survive today, their influence echoes through subsequent generations. The most metal-poor stars we observe, with less than 1,000th the Sun's metallicity, represent the second generation, stars that formed from gas, barely enriched by that first stellar generation. Your journey would take you past these ancient suns, each one a fossil from the universe's childhood, carrying information about conditions in the early cosmos. 39 minutes into your journey, 2,340 light-years from home, you'd witness the galaxy's magnetic field in action. While invisible to optical telescopes, this vast magnetic structure shapes cosmic processes on all scales. Synchrotron radiation from electrons spiraling around magnetic field lines creates the radio glow we observe from the galaxy. Dust grains align with magnetic fields, polarizing starlight and revealing the field's structure. Even star formation is influenced, as magnetic pressure can support clouds against gravitational collapse. The origin of galactic magnetic fields remains one of astronomy's unsolved mysteries. Did they arise from primordial seed fields amplified by dynamo action? Were they generated by the first stars and then spread throughout the galaxy? Recent observations by the SOFIA Airborne Observatory, which detected magnetic fields in distant galaxies, suggest these fields are fundamental features that have shaped galactic evolution since early cosmic times. 40 minutes out, 2,400 light-years traveled, you'd be passing through regions where stellar evolution creates some of nature's most precise clocks. Millisecond pulsars, neutron stars spinning hundreds of times per second keep time with precision rivaling atomic clocks. The pulsar PSR J0437475 rotates 576 times per second, its lighthouse beam of radiation sweeping across space with mechanical regularity. These cosmic timekeepers have enabled some of physics' most stringent tests. Observations of binary pulsars have confirmed Einstein's general relativity to extraordinary precision, including the detection of gravitational wave energy loss decades before LIGO's direct detection. Pulsar timing arrays now search for gravitational waves from supermassive black hole mergers by looking for tiny variations in pulse arrival times. Your journey might take you through the beam of such a pulsar, experiencing a cosmic lighthouse that has been flashing for millions of years. 41 minutes into your impossible voyage, 2,460 light-years from Earth, you'd encounter regions where dark matter's influence becomes undeniable. The rotation curves of our galaxy, how orbital speeds vary with distance from the center, can only be explained if the visible matter is embedded in a much larger halo of invisible dark matter. This mysterious substance, which interacts only through gravity, outweighs normal matter by a factor of 5 throughout the universe. Experiments deep underground search for dark matter particles, while astronomers map its distribution through gravitational lensing and stellar motions. The Gaia Space Telescope's precise measurements of over 1 billion stars have revealed subtle patterns that trace the dark matter distribution in unprecedented detail. Your journey would take you through this invisible sea, its presence felt only through its gravitational effects on the visible matter around you. 42 minutes out, 2,520 light-years traveled, you'd be witnessing stellar metamorphosis on grand scales. Asymptotic giant branch stars, the final evolutionary stage of stars like our Sun, pulsate and shed their outer layers, enriching the interstellar medium with carbon, nitrogen, and S-process elements formed by slow neutron capture. These stars are cosmic alchemists, creating many of the elements essential for life as we know it. The Atacama Large Millimeter Array has imaged the spectacular shells and spirals created as these dying stars shed their atmospheres. Some show evidence of unseen companions, planets or brown dwarfs that shape the outflowing gas into beautiful, complex patterns. Your impossible speed would let you watch millions of years of stellar evolution compressed into moments, seeing stars transform from stable suns to planetary nebulae before your eyes. 43 minutes into your journey, 2,580 light-years from home, you'd encounter regions where cosmic rays, high-energy particles accelerated by supernovae and other violent events, fill space with an invisible storm of radiation. These particles, mostly protons but including all elements up to iron and beyond, carry information about the galaxy's most energetic processes. Some cosmic rays have energies millions of times greater than anything producible in human particle accelerators. The Fermi Gamma Ray Space Telescope has revealed that cosmic rays interact with interstellar gas to produce gamma rays, creating a diffuse glow throughout the galaxy. This cosmic ray sea influences everything from star formation to the evolution of life. High-energy particles can trigger chemical reactions in molecular clouds, destroy complex molecules, and even influence planetary climates. Your journey through this particle storm would be like sailing through an invisible hurricane of matter and energy. 44 minutes out, 2,640 light-years traveled, you'd be passing through regions where the galaxy bears scars from ancient catastrophes. Superbubbles, cavities hundreds of light-years across, blown by multiple supernovae, reveal where clusters of massive stars lived and died together. The local bubble, within which our Sun currently resides, is one such structure, carved out by stellar explosions over the past 10 to 20 million years. These bubbles don't exist in isolation, but form a cosmic foam throughout the galactic disk. Where bubbles meet, gas compresses and new stars form. The Orion-Eridanus superbubble, spanning over 1,000 light-years, shows this process in action. Your journey would reveal how stellar death creates the conditions for stellar birth, a cycle of creation and destruction that has shaped the galaxy for billions of years. 45 minutes into your impossible voyage, 2,700 light-years from Earth, you'd encounter one of the galaxy's most enigmatic phenomena: hypervelocity stars racing through space at speeds exceeding the galactic escape velocity. These stellar speedsters, moving at hundreds or even thousands of kilometers per second, are cosmic refugees fleeing some violent event in their past. The star US 708 blazes through the galaxy at 1,200 kilometers per second, fast enough to escape the Milky Way entirely. The mechanisms that accelerate these stars to such extreme velocities tell stories of cosmic violence. Some were part of binary systems that ventured too close to the supermassive black hole at the galactic center. When one star was captured, its companion was flung outward like a stone from a sling. Others gained their speed from supernova explosions in binary systems, where the detonation of one star gives its companion a tremendous kick. Your journey might cross paths with these stellar exiles, racing toward intergalactic space. 46 minutes out, 2,760 light-years traveled, you'd be passing through regions where stellar collisions create objects that challenge our understanding of stellar evolution. Blue stragglers, stars that appear younger than their neighbors despite forming at the same time, reveal that stars can merge and be rejuvenated. In the dense cores of globular clusters, such collisions happen regularly on cosmic timescales, creating stars that burn hotter and bluer than they should. Recent simulations on supercomputers have revealed the incredible complexity of these stellar mergers. As two stars spiral together, their outer layers mingle and mix, creating temporary structures of extraordinary beauty: spiral arms, tidal tails, and shells of ejected material. The final merged star often rotates rapidly, sometimes close to the speed where centrifugal force would tear it apart. These cosmic amalgamations represent natural experiments in stellar physics that we could never reproduce in laboratories. 47 minutes into your journey, 2,820 light-years from home, you'd witness the galaxy's chemical enrichment happening in real time. Each supernova explosion disperses several solar masses of heavy elements into space, enriching the surrounding medium for future generations of stars. Type-Ia supernovae, the thermonuclear detonation of white dwarfs, are particularly important for creating iron peak elements. These standard candles not only help us measure cosmic distances, but also serve as the universe's iron foundries. The rate of chemical enrichment varies dramatically across the galaxy. In the galactic bulge, where star formation was intense in the past, stars can have metallicities exceeding our sun's. In the outer halo, where star formation has always been sparse, stars remain remarkably pristine. Your journey would take you through this chemical gradient, witnessing how billions of years of stellar evolution have transformed primordial hydrogen and helium into the rich periodic table we know today. 48 minutes out, 2,880 light-years traveled, you'd encounter stellar nurseries where the next generation of stars and planets is forming right now. The Eagle Nebula's pillars of creation, made famous by Hubble Space Telescope images, represent just one small region where gas and dust are collapsing to form new stars. Within these pillars, dense knots of material are contracting under their own gravity, heating up as they shrink, preparing to ignite nuclear fusion and join the stellar population. The The James Webb Space Telescope has peered through the dust of these stellar nurseries, revealing protostars and protoplanetary disks invisible to optical telescopes. Some disks show gaps and rings, evidence that planets are already forming even as their host stars are still gathering mass. The chemistry in these disks is remarkably complex, with water, methanol, and even more complex organic molecules detected. Your impossible journey would compress millions of years of star and planet formation into seconds of observation. 49 minutes into your impossible voyage, 2,940 light-years from Earth, you'd be passing through regions where stellar winds sculpt the interstellar medium on vast scales. Wolf-Rayet stars, the exposed cores of massive stars that have blown away their outer layers, have winds reaching 3,000 kilometers per second. These winds carry away solar masses of material over just hundreds of thousands of years, enriching space with carbon, oxygen, and other fusion products. When these stellar winds collide with the surrounding medium, they create stunning structures visible across the electromagnetic spectrum. Bow shocks mark where fast-moving stars plow through space. Wind-blown bubbles surround the most massive stars. Where winds from multiple stars interact, complex structures form, arcs, filaments, and shells that glow in optical, infrared, and X-ray light. The Chandra X-ray Observatory has revealed that these wind-blown regions can reach temperatures of millions of degrees, hot enough to emit copious X-rays. 50 minutes out, nearly an hour into your journey, you've traveled 3,000 light-years from Earth. At this distance, you'd be encountering regions where the galaxy's spiral structure becomes clearly apparent. The Perseus arm, one of the galaxy's major spiral features, would be revealing its true nature not as a material structure but as a wave phenomenon. Stars and gas clouds orbit the galactic center at different rates, temporarily bunching up in the spiral arms before spreading out again. The nature of spiral arms remained mysterious for decades after their discovery. Why don't they wind up over time as inner stars orbit faster than outer ones? The answer lies in density wave theory, developed in the 1960s by C.C. Lin and Frank Hsu. Spiral arms are like cosmic traffic jams, regions where orbiting material slows down and bunches up before moving on. This explains why star formation is enhanced in spiral arms. The compression of gas clouds as they enter the density wave triggers gravitational collapse 51 minutes into your journey, 3,060 light-years from home. You'd witness how supernovae shape galactic evolution on grand scales. Each explosion injects enormous energy into the interstellar medium, typically 10 to the 51st ergs, equivalent to the Sun's entire energy output over 10 billion years released in seconds. This energy doesn't just disperse heavy elements, it drives turbulence, heats gas to millions of degrees, and can trigger or suppress star formation across entire regions. Supernova remnants like Cassiopeia A, observed in detail by the Chandra X-ray Observatory and the Spitzer Space Telescope, reveal the complex physics of these expanding blast waves. Particles are accelerated to cosmic ray energies at the shock fronts. Dust grains are destroyed and reformed. Molecules are dissociated, and new ones form in the cooling gas behind the shock. Your journey might take you through such a remnant, experiencing firsthand the awesome power of stellar death. 52 minutes out, 3,120 light-years traveled, you'd encounter planetary systems in every stage of evolution, young systems still embedded in their natal gas and dust, where planets migrate through their disks and jostle for position, mature systems like our own, where dynamics have settled into stable configurations, ancient systems where host stars have evolved off the main sequence, subjecting their planets to new challenges as stellar luminosity and mass loss reshape orbits. 53 minutes into your impossible voyage, 3,180 light-years from Earth, you'd be witnessing the aftermath of one of the galaxy's most recent cosmic catastrophes. The Vela supernova remnant, created by a stellar explosion approximately 11,000 years ago, still expands into space at thousands of kilometers per second. The Vela pulsar at its heart, spinning 11 times per second, serves as a cosmic lighthouse marking where a massive star met its violent end. This pulsar powers a spectacular pulsar wind nebula, where particles accelerated to near light speed create a glowing cloud visible in X-rays. The interaction between the pulsar wind and the supernova remnant creates complex structures, jets, wisps, and rings that change on timescales of years. Your impossible speed would let you watch these structures evolve, seeing decades of motion compressed into heartbeats. 54 minutes out, 3,240 light-years traveled, you'd encounter evidence of the galaxy's ongoing chemical evolution written in the compositions of stars of different ages. The oldest stars in this region formed 10 billion years ago when the galaxy's metallicity was much lower. Younger stars show progressively higher abundances of heavy elements, recording how successive generations of supernovae enriched the interstellar medium. If you are still watching, make sure to subscribe to the channel and give this video a like. Your support means a lot to me. The Galaxies survey, using the Anglo-Australian telescope, has measured detailed chemical abundances for over 500,000 stars, creating a chemical map of our galactic neighborhood. Each star's composition tells a story, not just of when it formed, but potentially where. Stars that form together in the same molecular cloud share chemical fingerprints, allowing astronomers to identify stellar siblings separated by billions of years of galactic orbits. 55 minutes into your journey, 3,300 light-years from home, you'd be passing through regions where binary star evolution creates some of nature's most exotic objects. Cataclysmic variables, binary systems, where a white dwarf steals matter from a companion star, undergo dramatic outbursts as accumulated material undergoes thermonuclear fusion on the white dwarf's surface. These nova explosions can increase the system's brightness by factors of thousands in just days. Some of these systems are on death spirals, with orbital periods measured in minutes rather than hours or days. The binary system HM Cancri has an orbital period of just 321 seconds. The two white dwarfs orbit each other in less time than it takes to soft-boil an egg. These systems emit gravitational waves that will eventually cause them to merge, possibly triggering a Type Ia supernova or creating a more massive white dwarf. 56 minutes out, 3,360 light-years traveled, you'd witness regions where the interstellar medium reveals its true complexity. Far from being empty, the space between stars contains intricate structures shaped by stellar winds, magnetic fields, and turbulence. High-velocity clouds of gas, some containing the mass of millions of suns, plow through the more diffuse medium at hundreds of kilometers per second. The origins of these clouds remain mysterious. Some may be material falling into the galaxy for the first time, while others might be galactic fountains of gas blown out by supernovae and falling back. The Smith Cloud, currently approaching the Milky Way at 270 kilometers per second, contains enough gas to form millions of stars when it collides with the galactic disk in about 30 million years. Your journey might take you through similar clouds, experiencing the complex chemistry that occurs when gas phases of different temperatures and densities interact. 57 minutes into your impossible voyage, 3,420 light-years from Earth, you'd encounter stellar streams that trace the galaxy's history of mergers and interactions. The Arcturus stream, a group of stars sharing similar motions and compositions, likely represents the remains of a satellite galaxy absorbed billions of years ago. These stars move through the galaxy on similar orbits, preserving a fossil record of their common origin. The precision of modern spectroscopy allows astronomers to identify stream members through subtle similarities in their chemistry and motion. The Gaia Space Telescope has revolutionized this field, revealing dozens of previously unknown streams threading through the solar neighborhood. Your journey would take you across these stellar rivers, each one telling a story of galactic cannibalism and evolution. 58 minutes out, 3,480 light-years traveled, you'd be passing through regions where brown dwarfs blur the line between stars and planets. These failed stars, not massive enough to sustain hydrogen fusion, populate the galaxy in vast numbers. The WISE infrared telescope has revealed thousands of these objects, including some with temperatures cooler than a summer day on Earth. These Y-class brown dwarfs challenge our definitions of what constitutes a star versus a planet. Some brown dwarfs show weather patterns remarkably similar to gas giant planets, cloud bands, storms, and even aurora. The Spitzer Space Telescope created weather maps of several brown dwarfs, revealing that these objects have complex atmospheric dynamics despite not being true stars. Your journey might take you past brown dwarf binary systems, where two failed stars orbit their common center of mass in cosmic solitude. 59 minutes into your journey, 3,540 light-years from home, you'd witness regions where star clusters dissolve into the galactic field. Open clusters, born from the same molecular cloud, gradually disperse as gravitational interactions with giant molecular clouds and the galactic tidal field pull them apart. The Hyades cluster, visible to the naked eye in the constellation Taurus, is currently in the process of dissolution, its stars spreading along a stream hundreds of light-years long. By studying these dissolving clusters, astronomers learn about the galaxy's gravitational field and the distribution of dark matter. The rate at which clusters evaporate depends on their mass, their orbits, and encounters with massive objects. Your impossible speed would let you watch this evaporation process, seeing stellar families slowly separate and join the general galactic population. 1 hour into your impossible voyage, 60 minutes of traveling at 1 light-year per second, you've covered 3,600 light-years. At this distance from Earth, you'd be approaching the far side of the Orion Spur, the minor spiral arm that contains our solar system. The galaxy around you would be revealing its true three-dimensional structure, not the flattened view we see from Earth, but a complex, dynamic system of stars, gas, and dark matter, all participating in a cosmic dance that has continued for over 13 billion years. The perspective gained from this impossible journey transforms your understanding of humanity's place in the cosmos. Every star you've passed potentially hosts planets where matter has organized itself into ever more complex forms. Some of these worlds might harbor life, perhaps even civilizations contemplating their own cosmic journeys. The atoms in your body have participated in this galactic evolution, cycling through generations of stars before becoming part of you. As you continue racing through the galaxy at impossible speeds, you carry with you the knowledge that you are not separate from this cosmic grandeur, but an integral part of it. The same physical laws that govern the birth and death of stars also enabled the chemistry of life. The same gravitational forces that shape galaxies also helped form the solar system where consciousness could emerge. You are the universe becoming aware of itself, using arrangements of stellar matter to contemplate the very processes that created that matter billions of years ago. As you continue your impossible journey beyond the 1 hour mark, having traveled over 3,600 light-years from Earth, the true magnitude of what you're witnessing begins to crystallize. You're not just observing distant objects, you're experiencing the universe as a living, breathing entity where every component influences every other component across vast scales of space and time. The galaxy reveals itself not as a collection of isolated stars, but as an integrated ecosystem where matter, energy, and information flow in patterns of breathtaking complexity. 61 minutes out, 3,660 light-years traveled. You'd encounter regions where the galaxy's magnetic field creates structures invisible to optical telescopes but revealed by radio astronomy. Synchrotron radiation from cosmic ray electrons spiraling around magnetic field lines traces out the galaxy's magnetic architecture. This invisible scaffolding influences everything from star formation to the propagation of cosmic rays, yet it remains one of the least understood components of galactic structure. The Planck Space Telescope has mapped polarized emission from dust grains aligned with magnetic fields, revealing that these fields are not random but show organized patterns on galactic scales. Some regions show field lines following spiral arms, while others reveal more chaotic structures shaped by stellar winds and supernova explosions. Your journey through these magnetic landscapes would be like sailing through invisible currents that have shaped galactic evolution for billions of years. 62 minutes into your voyage, 3,720 light-years from home, you'd witness how the galaxy maintains its spiral structure despite the differential rotation that should wind it up over time. The answer lies in the complex interplay between density waves, stellar feedback, and magnetic fields. Spiral arms aren't permanent features but transient patterns that form, persist for hundreds of millions of years, then dissolve and reform. Computer simulations reveal that spiral patterns can be triggered by interactions with satellite galaxies, bars in galactic centers, or even random fluctuations in the stellar distribution. The Milky Way's spiral structure has likely changed dramatically over its lifetime, with arms appearing and disappearing as gravitational and hydrodynamic forces reshape the galactic disk. Your impossible speed would let you witness this cosmic choreography, seeing how temporary patterns create the illusion of permanent structure. 63 minutes out, 3,780 light-years traveled, you'd encounter evidence of the galaxy's most violent past. Stellar streams from disrupted globular clusters trace the orbits of these ancient stellar cities as they were torn apart by tidal forces. The Palomar 5 stream stretches for thousands of light-years, marking where a globular cluster has been slowly shredded over billions of years. These streams provide crucial information about the galaxy's dark matter distribution and gravitational field. The process of cluster disruption isn't uniform, but depends on the cluster's orbit, mass, and internal structure. Clusters on highly elliptical orbits experience stronger tidal forces during their closest approaches to the galactic center. Those with lower concentrations lose stars more easily than their more tightly bound cousins. Your journey might take you through multiple such streams, each one a fossil record of gravitational violence played out over cosmic time. 64 minutes into your impossible voyage, 3,840 light-years from Earth, you'd be witnessing stellar evolution in all its magnificent variety. Red supergiants approaching the ends of their lives, their surfaces cool enough for complex molecules to form in their extended atmospheres. Blue hypergiants, the most massive stars known, burning through their nuclear fuel so rapidly that they can barely hold themselves together against their own radiation pressure. The most extreme examples push the boundaries of what's physically possible. The Pistol Star, one of the most luminous stars known, emits as much energy in 6 seconds as our Sun does in a year. Eta Carinae, a luminous blue variable, underwent a massive eruption in the 1840s that briefly made it the second brightest star in Earth's sky. These stellar monsters live fast and die young, but their brief lives profoundly influence their galactic neighborhoods. 65 minutes out, 3,900 light-years traveled, you'd encounter regions where the search for extraterrestrial intelligence takes on new dimensions. At your impossible speed, you'd be passing through the expanding shells of radio and television signals from countless civilizations, if they exist. The first television broadcasts from Earth, transmitted in the 1930s, have now reached stars within about 90 light-years. Any civilizations in this region could, in principle, be watching our earliest TV shows right now. But the galaxy is vast, and even at light speed, communication between civilizations, separated by thousands of light-years, would require patience measured in millennia. Perhaps advanced civilizations use entirely different communication methods, gravitational waves, neutrino beams, or techniques we haven't yet imagined. Your journey might take you through regions where such communications are happening right now, invisible to our current technology, but representing conversations between minds separated by cosmic distances. 66 minutes into your journey, 3,960 light-years from home, you'd witness how cosmic recycling operates on galactic scales. The interstellar medium isn't static but flows in complex patterns driven by stellar winds, supernova explosions, and galactic rotation. Gas blown out of the galactic disk by stellar feedback can travel thousands of light-years before falling back, enriched with heavy elements and carrying energy from stellar processes. This galactic fountain model explains many observed features of the interstellar medium. High-velocity clouds approaching the galaxy might be material returning from previous episodes of star formation. The thick disk population of stars might have formed from gas that was processed through this fountain cycle. Your impossible journey would reveal these flows in action, showing how the galaxy breathes, inhaling primordial gas and exhaling enriched material in cycles that span hundreds of millions of years. As you approach the 70-minute mark of your impossible voyage, having traveled over 4,000 light-years from Earth, the profound implications of what you've witnessed begin to sink in. You've seen the universe not as a collection of separate objects, but as an integrated system where every component influences every other component. The carbon in your DNA was forged in stellar cores you've passed. The iron in your blood was dispersed by supernovae whose remnants you've encountered. The calcium in your bones was created in stellar furnaces that died billions of years ago. This cosmic perspective transforms your understanding of what it means to be human. You are not separate from the universe, but an integral part of its ongoing evolution. The same physical laws that govern stellar birth and death also enabled the chemistry of life. The same gravitational forces that shape galaxies also helped form the solar system where consciousness could emerge. You are the universe becoming aware of itself, using arrangements of stellar matter to contemplate the very processes that created that matter. The journey at 1 light-year per second reveals that the universe is not just vast but magnificently interconnected. Every photon reaching your eyes carries information about cosmic processes operating across enormous ranges of scale and time. Every atom in your body has participated in cosmic evolution, cycling through multiple generations of stars before becoming part of you. The story of the cosmos is also your story, written in the language of physics and chemistry across billions of years. As your impossible journey continues beyond the bounds of this exploration, you carry with you a transformed perspective on existence itself. The night sky is no longer a distant backdrop, but a dynamic arena where cosmic evolution continues to unfold. Every star represents a nuclear furnace, creating the elements necessary for complexity and life. Every galaxy contains billions of such furnaces, each one a potential birthplace for worlds where matter might organize itself into forms we can barely imagine. The universe revealed by traveling at 1 light-year per second is not cold and empty, but warm with possibility, rich with complexity, and pregnant with potential. In contemplating these cosmic scales and processes, you participate in the universe's own quest for self-understanding. You are both observer and participant, student and subject, in the grandest story ever told, the story of how the universe evolved from simplicity to complexity, from uniformity to diversity, from unconsciousness to awareness. This cosmic journey reminds us that we are made of star stuff, that our questions are universal, and that science is humanity's greatest adventure. In reaching across impossible distances at impossible speeds, we discover not just the universe's magnificent scale, but our own magnificent place within it. We are the cosmos awakening to its own wonder, using the very atoms forged in stellar cores to contemplate the processes that created those atoms. In understanding the universe, we understand ourselves, for we are not separate from the cosmic story, but its most remarkable chapter yet written. But if you have ever wondered how long we could survive real interstellar travel, click the video on the screen. The real horror of interstellar travel isn't the vast distance, it's what deep space does to the human body and mind. In this video, we break down the brutal biological, psychological, and physical barriers that make human interstellar travel practically impossible.